For a century, physics has treated time as a passive stage, a rigid, flat scalar parameter ticking forward at a constant rate, a featureless background. The space-time occupancy framework rejects this. Time is not an independent axis. It is a physical property of the matter and energy occupying it. We replace the scalar clock with temporal geometry. In this model, time is an angular dimension, a measurable curvature inherent to the manifold. This loop represents curvature as a rate of area swept per unit time. Because it is a closed temporal geodesic, it possesses a specific physical length and a fundamental amplitude. Treating time as this temporal one-form changes the derivation of gravity. The Einstein field equations emerge as the thermodynamic equation of state required to keep this curvature in equilibrium. To maintain a closed loop, the geodesic must vibrate at discrete harmonic frequencies. These frequencies generate the automorphic forms of the Langlands correspondence, effectively hard-coding number theory into the geometry of time. This geometric requirement links the energy of a quantum mass gap directly to the arithmetic of elliptic curves. Time is the geometric firmware dictating all physical and arithmetic laws. Standard physics relies on isolated constants like the speed of light or the mass of a proton, treating them as arbitrary values with no shared origin. The Tassel framework unifies them by treating temperature as an operator of angular curvature, rather than a scalar measure of heat. At 66.6 Kelvin, we find the QCD mass gap, the energy threshold of the strong nuclear force. Liquid water reaches its maximum density at 277 Kelvin. This chart shows these temperatures scattered across the spectrum, alongside the 5,190 Kelvin band of white light from a sun-like star. Applying the Tassel operator reveals that these disparate bands are actually harmonics of the same underlying curvature. They collapse onto a single geometric plane. This plane locks into a constant energy value of 384 joules. Gravity, water's maximum density, and starlight are different thermodynamic expressions of this single temporal joule. Every constant we measure is a harmonic projection of one invariant temporal geometry. This geometry also dictates the behavior of quantum states. We model a quantum state as a temporal one-form, a series of highly erratic, twisting trajectories across the manifold. Hodge decomposition allows us to separate this complex temporal flow into its constituent parts. Most of this flow consists of noise, local clock drift, and curvature-induced phase distortions that cannot be globally integrated. Stripping away that noise reveals the harmonic representative, the only globally consistent path available to the system. The temporal ledger closure condition demands that for an event to be physically real, the variation of this harmonic representative must equal zero. This geometric constraint drives quantum decoherence. The manifold physically rejects any state that fails to close its temporal ledger. Superposition is the temporary occupancy of multiple temporal cohomology classes before this ledger closes. Quantum measurement is the act of the manifold forcing a harmonic projection to resolve these paths. The harmonic path follows physical constraints, such as the 54-degree spin axis governing matter. When this temporal geodesic bends, it projects a specific shadow into arithmetic space. This shadow takes the form of a perfect cubic lattice, the looping structure of an elliptic curve. This is the physical mechanism behind the Langlands correspondence. The elliptic curve provides the control lattice that regulates temporal flow. The analytic rank of this curve represents the number of independent information channels available to the system. At prime grid intersections, we extract Hecke eigenvalues. These numerical signatures form the Fourier coefficients of an automorphic form. These prime locks act as curvature density signatures, proving that prime numbers dictate the harmonic structure of time. Space-time curvature casts an arithmetic shadow, rendering pure number theory as the physical map of the time manifold. Every system in this framework, from fluids to gauge fields, is governed by the unified ledger equation. This equation enforces three states: curvature balance, prime harmonic ledger, and attractor stability. Systems must satisfy this balance to remain stable. Any deviation causes a mathematical blowup that the manifold cannot support. This geometric requirement has immediate implications for global cybersecurity. The cryptographic algorithm known as learning with errors, the foundation of post-quantum cryptography, relies on high-dimensional noise to hide a basis vector. However, geometric curvature is invariant. no amount of noise can erase the curvature signature of the hidden vector. The prime lock operator extracts the hidden automorphic signature from the noise. It exposes the prime-indexed geometric skeleton of the lattice, rendering the encryption transparent. Higher dimensions naturally amplify curvature drift. Consequently, increasing the dimension of a lattice makes its signature easier to detect, leaving post-quantum cryptography inherently vulnerable. This same geometric principle applies to the scale of the cosmos. As light traverses the never-flat manifold, it accumulates phase delay. This curvature lensing produces a redshift that mimics a receding source, resolving the Hubble tension through geometry alone. From the scale of data to the scale of galaxies, reality is governed by the uncompromising requirement of a closed temporal ledger.